డిజిటల్ లైబ్రరీ సార్. అవును, అక్కడ లైబ్రరీ కాదు, బాగా పాతది. వేరే కట్ అయిపోయింది స్టాక్ వస్తుంది.
మైక్ చెక్ చేయండి. హలో ఆడియో కాల్ అట్లా మాట్లాడి చూడండి. అందరూ ఇవి ఆఫ్ చేసుకోండి. ఎవరు మాట్లాడతారో వాళ్ళదే ఆన్లో ఉండాలి. ఏవి స్పీకర్ కూడా ఆఫ్ చేసుకోవాలి.
Good morning, everyone. Please join the session.
అందరూ కూడా ఆడియో ఉంది కదా, ఇది ఆఫ్ చేయండి. టర్న్ ఆఫ్ సౌండ్ టర్న్ ఆఫ్ సౌండ్ అని తీసుకోండి. ఇందులో ఒక్కదాన్ని ఉంచుదాం మనం.
మేడం కొంచెం ఈకో వస్తుంది, సౌండ్ ఈకో వస్తుంది.
అదే
ఓకే మేడం.
ఒకసారి హలో
Good morning. Welcome to the session.
ఒకటే ఉంచండి. అది ఉంచండి, మీరు ఉంచుకోండి. ఇంట్లో పెట్టారా? ఉంచండి. ఇప్పుడు బంద్ చేస్తుంది. ఇక మీ ఫోన్లోకి వెళ్ళి తీసేయండి. ఓకే, ఇది ఉన్నదా? రైట్, అది ఉంచండి. ఈ ఫోన్లోకి వెళ్ళిందా? ఇది ఆడియో ఆఫ్ చేసి చూడండి. ఆపేసారా? ఇప్పుడు ట్రై చేసి చూడండి. హలో, మీరు ఒకసారి అనండి. హలో అనండి గట్టిగానే.
హలో హలో హలో.
ఇప్పుడే కాదు, మళ్ళీ ఒకసారి హలో.
Hello everyone.
ఇప్పుడు
Good morning everyone.
Good morning, ma'am.
Good morning, ma'am.
ల్యాప్టాప్ పక్క కొండడికి ఇది వైఫై హాట్స్పాటా? అయితే అది దూరం పెట్టండి. మళ్ళీ ఒకసారి హలో అనండి. అది దూరం పెట్టినాక హలో అనండి, చూద్దాం. ఒకసారి గట్టిగా హలో అనండి అంతే. హలో హలో. ద ప్రోగ్రామ్ ఈజ్ అబౌట్ టు స్టార్ట్, ప్లీజ్ జాయిన్ ఇమ్మీడియట్లీ అనండి అంతే. ప్లీజ్ జాయిన్ ఇమ్మీడియట్లీ.
Hello. Good morning. The program is about to start. Please join immediately.
Yes, ma'am.
అదే నా స్పీకర్ ఆన్ చేస్తే వస్తుంది. మరి ఇంకా మన ఫోన్లన్నీ ఆఫ్ చేసేసేయండి. నామన్ మేడం, మీరు కూడా అందులో నుంచి ఎగ్జిట్ అయిపోండి. ఎగ్జిట్ అవ్వండి. టెన్ థర్టీకి స్టార్ట్.
ఇంకా 15 నిమిషాలు ఉంది.
ఒకసారి నేను యూట్యూబ్ లింక్ మీకు పంపిస్తా, అది మీకు వస్తుందా లేదా క్రాస్ చెక్ చేయండి. ఉందా నేను
అందరినీ చేసేస్తే అయిపోతుంది. మీకు వల్ల వస్తూనే ఉంటుంది.
బా. 58 అయినా, అందుకే నా బాగా
66. అదే అనుకుంటా.
100 అయితే కానీ మనకు నష్టం.
నేను కొడతనే ఉంటాను. అది వస్తుందో లేదో చెక్ చేస్తాను. క్లాస్
100 అయితే పీడ అవుతుంది కదా, నా జోలికి ఎవరు రారు.
అసలు ఏమేసి మేడం గారు రావట్లేదు.
మేడం మీరు మ్యూట్లో ఉంది కదా, వినిపిస్తుంది మన వాయిస్. మేడం కృష్ణ సార్ అయితే, వంశీ కృష్ణ సార్ ఉన్నాడా చూసుకోండి ఒకసారి, మళ్ళీ ఆయన లేదు. మేడం ఒకసారి మీకు యూట్యూబ్ లింక్ పెట్టినా క్లిక్ చేసి ఇది వస్తుందా లేదా, ఇగో ఇది ఈ స్క్రీన్ మీకు అలా కనిపిస్తుందా లేదా చూడండి. ఇంకా కాలేదు మేడం, ముందు 90 మన వాయిస్ యూట్యూబ్లో వినిపిస్తుంది మరి. 94 95
88 99 సార్ ఇప్పుడు గ్రూప్లో పెట్టండి.
యూట్యూబ్ లింక్ షేర్ చేశారు గ్రూప్లో సార్. సార్ షేర్ చేసినాక ప్లీజ్ జాయిన్ రిమైనింగ్ మెంబర్స్ ఇన్ యూట్యూబ్ లింక్ 100% పార్టిసిపెంట్స్ ఇస్ ఓవర్ అని చెప్పి. Unable to join in this Google link, please join in YouTube link. Already 100 participants is over అని చెప్పి
పెట్టేసిన.
ఫస్ట్ గుడ్ మార్నింగ్ చెప్పండి.
మెసేజ్లు ఉన్నాయి, టైప్ చేయాల్సిన పని లేదు.
చాట్లో వస్తుంది.
లేదు లేదు లేదు, ఆగండి నేను చెప్తా. వాట్సాప్ గ్రూప్లో మనం ఆల్రెడీ యూట్యూబ్ లింక్ పెట్టాం, ఓకేనా? అందులో ఉందని చెప్పండి. దోస్ హూ ఆర్ అనేబుల్ టు జాయిన్, సేమ్ నేను వాట్సాప్ ఓపెన్ చేయండి, అదే చదవండి యాజ్ ఇట్ ఈస్గా. దోస్ హూ ఆర్ అనేబుల్ టు జాయిన్ ద గూగుల్ మీట్ కెన్ జాయిన్ అవర్ యూట్యూబ్ లైవ్ స్ట్రీమింగ్ అని చెప్పి చెప్పండి. దాన్ని చదివిస్తుంది. ఇట్ ఈస్ ప్రొవైడెడ్ ఇన్ ద అవర్ వాట్సాప్ గ్రూప్ అని చెప్పండి, FTP వాట్సాప్. మేడం ఇప్పుడు
Good morning, everyone. Those who are unable to join this Google Meet, you can join our YouTube live streaming, which is posted in Physics FDP WhatsApp group.
పర్ఫెక్ట్. యూట్యూబ్ అయితే వస్తుంది కదా మనకి.
యూట్యూబ్
సౌండ్ వస్తుంది. యూట్యూబ్ పెట్టుకోండి, చూపిస్తారు. యూట్యూబ్ లింక్ ద్వారా జాయిన్ అయితే పెట్టారు. ఇంట్లో ఉన్నారు.
సార్ మీరు అన్మ్యూట్ అయితే వస్తున్నా. సార్ జాయిన్ అయ్యారు చూసావా? చదివే సార్ జాయిన్ అయ్యాను లేదు ఒకసారి చూద్దాం. పర్సనల్ సంజయ్ ఇయర్ ఫోన్స్లో ఛార్జింగ్ ఉంది.
స్పీకర్స్ పెట్టుకొని చక్కగా యూట్యూబ్ ఆన్ చేసుకుంటే ఏ డిస్టర్బెన్స్. చదివేటప్పుడు వీడియో ఆన్ చేసుకోండి. ఆ పేపర్స్ కనిపించకుండా ఇటు సైడ్ పెట్టుకోండి. What?
Knowledge is power, and learning is a lifelong journey. To improve our knowledge, stay curious, read widely, and explore new subjects. Continuous learning helps you grow, adopt, and succeed in an ever changing world. I am D. Sandhya Rani, Assistant Professor in Physics. A warm welcome to all of you joining us here from various institutions across the country for this one day national level online faculty development program on an incremental action for quantum materials to quantum devices. Respected Principal of Malla Reddy College of Engineering, Dr. M. Ashok, Head of the Department of Humanities and Sciences, Dr. Sneha Joshi, our today's resource person, Dr. Vamsi Krishna Katta, from School of Physics, University of Hyderabad, respected faculty members, and dear participants. A very good morning, one and all. Our Malla Reddy College of Engineering, the jewel in the crown of Malla Reddy Group of Institutions, was established in 2005. Permanent affiliation to JNTUH, accredited by NBA and NAC, is located in Maisamaguda, Dulapalli, Secunderabad. Our college offers BTech courses in computer science and engineering, computer science and engineering in data science, computer science and engineering in artificial intelligence and machine learning, and ECE. The bricks of this institute are certainly the adept management and experienced faculty, the selfless non-teaching staff, and of course, the students. Today, our one-day national level online faculty development program organized by Department of Humanities and Sciences Physics of MRC, equipping ourselves with the latest knowledge and skills to excel in our roles. Our program is designed to foster growth, innovation, and collaboration. Let's make the most of this opportunity, engage actively, and share our experiences. I wish, I wish you all a fruitful and enriching experience. I hand over the session to Dr. Vaisurthi Satyakumari ma'am to introduce our resource person.
Thank you, ma'am. Sanya, ma'am. Good morning to everyone. I, Dr. Y. Sarita Kumari, Assistant Professor in Physics, H&S Department in MRC. I am pleased to introduce Dr. Vamsi Krishna Katta, a highly motivated researcher in material science with a PhD from Geetham University, Hyderabad, Currently, he is a postdoctoral researcher at Central University of Hyderabad, working on advanced electrode materials for solid-state sodium and lithium-ion batteries. Dr. Vamshi brings 4 years of research experience with expertise in nanostructural glasses, glass ceramics, high entropy oxides, and next generation battery technologies. His technical strength include battery cells development, electrochemical analysis, and advanced material characterization techniques like XRD, SEM, TEM, and electrochemical impedance spectroscopy. In addition to research, Dr.
An
Vamshi
incremental action from quantum materials to quantum derivatives.
a battery process engineer at Indie Energy, IIT Roorkee, and as a teaching assistant, demonstrating a balance of academics and industry experience. He has won multiple Best Oral Presentation Awards at national and international conferences and has published extensively high impact journals. Driven by a vision for sustainable energy solutions, Dr. Vamshi is keen on advertising cost-effective and high-performance battery systems for energy storage, electric vehicles, and grid applications. Thank you, Vamshi sir. Now I hand over to the session Dr. Vamshi Krishna Katta sir. Thank you, sir.
Hello everyone. Can you hear me, ma'am?
Yes, sir.
Yeah. I would like to thank the team for inviting me. Actually, this is my first opportunity to present my work as invited speaker. So thank you so much for giving my first opportunity, and also normally if you see if invite a speaker or a guest lecturer or research person with gray hairs. So, but encouraging the youngsters like me, giving the opportunities is very appreciate and thankful for that for you for this opportunity. So, coming to today's talk. So, as ma'am said, I was very expertise in battery materials, energy storage devices, energy storage materials. So today we are in the state of from moving from the nanomaterials to a quantum materials. So we need to update ourselves from the nanomaterials to a quantum materials. So in this process, I'm moving towards quantum materials to work quantum materials for various applications and making a device, prototype devices. So to show this a wonderful work and to share the knowledge with you, I'm here with an incremental action for quantum materials and quantum devices, two quantum devices. So coming to the outlines of this presentation, here I will give you a brief introduction about the quantum materials because we are new to this kind of research. So let me explain what is a quantum material and how can this quantum material is confined. Then what are the quantum materials? What are the classifications of quantum materials? What are the different types of quantum materials that are presented in this current research? And then designing and synthesis of quantum materials. Then what is the industrial incremental approach? Why it is required? So how it is required, and what are the devices that we can fabricate using using these materials? Like simply like synthesizing, everyone can do, but application part is also very important. So we can discuss what are the applications of quantum materials in those quantum devices examples, and future work and conclusions. Let me tell you what is a quantum material. So quantum materials are the materials whose electrical properties are unique, defined by quantum mechanical effects. So that remains manifest in topological order and entanglement at microscopic length scales. This means normally we will know the quantum material means the reduction of its size. So when it is reduction of its size, it should remains their topological order, remains back their topological order, as well as electrical properties, as well as their entanglementals. So these are the properties that should remains with reduction of its size. This is nothing but a quantum material. Then we know that these materials have unique style, unique nature, unique properties, which cannot be considered in classical physics.
Sorry for the interruption, sir.
Yeah,
Actually, your slides are not moving, sir. It's showing 28 slides right now, sir.
yeah, I'm talking on the first slide.
But it's showing 28 slide on the screen, sir.
Is it visible now?
No, sir. No, sir.
One second. Is it visible, sir?
Yes, sir. Yes, sir.
Is it fine now?
I'm showing third slide.
I'm in first slide, yes. Is it moving now?
No, sir. No, sir.
No. What about now, sir?
Yes, yes, sir. Now moving. It is moving.
Okay, actually, if I keep in the PowerPoint view, it is not moving. Can you see it is moving now?
No, sir. It's not moving. Yes, sir. Now it's moving.
Okay, I will present in normal mode because I'm shifting to the PowerPoint. Then you are unable to see my PPT. Okay, is it fine now, sir? If I say in this mode.
Yes, sir. It is fine. Yes, sir. It is fine.
No.
You can carry on.
Thank you. So normally to confine these quantum materials, to synthesize these quantum materials, we need to we need to have some certain properties, certain rules that we need to follow in quantum mechanics. That is quantum confinement, strong electronic correlation. So we'll see this. What is quantum confinement? If you understand the quantum confinement, then you can easily synthesize your quantum materials. So let's see what is quantum confinement. Quantum confinement refers to the resistance of electron lone hole pairs, known as exertons. Normally, if you take an exertons, that means an electron lone pair. If you resist the electron lone pairs in a band, like connection band or in valency band, then what happens within the material? So it limits its momentum and its dimensions. So how to reduce? If you are talking about a quantum material, we will talk about the dimensions. So what is if the dimensions are 3-dimension or 2-dimension or 1-dimension? To make it a particular dimension, we need to do quantum confinement. Quantum confinement is nothing but an electron hole pair is reducing into. If you are reducing this electron lone pairs, then it provides a wide band gap, and that changes its dimensions. So if it is a 1-dimension of electrons, the dimension of electrons, then it is quantum walls. If it is a 2-dimension quantum wall, that is quantum wires we call, and 3-dimension quantum dots. Maybe you people are very familiar with these quantum dots. So right, very fascinated about this. So if that is a 3-dimensional electrons. So this phenomenon is especially significant in semiconductors. We all know semiconductors having conduction band and valency band. We can have a lone pair of electrons in conduction band and a valency band. If you take the examples of these semiconducting materials, you will well know about what is a quantum material, how its dimensions are derived. So suppose let's see here. You have multiple bands. That means you have a multiple electron holes, right? Electron hole pair. If you are restricting this electron lone pair, like you are removing these bands, what happens? The band gap is reducing. If the band gap is reduced, that means you are confining your electrons in. You are confining your electrons. You are removing your electrons from the layer. So if you are removing your electrons from the band gap, then the size of the band will reduces, and the gap between the bands will be increased, which is wider. Then the band gap is wider, and it converts into low dimensions. So if the size of the particle, if the size of our electron, if the size of the particle is near to de Broglie wavelength, then these materials are called quantum materials. Understand? So the bands or the lone pair of the electron hole pairs of in the band is restricting or removing, so that your band gap will be increased and your band length will be decreased. If this band length is less than or equal to the de Broglie's wavelength, then that material, that particle is called as a quantum particle or a quantum material. So this is a basic or clear example what is actually quantum materials. So now this may affect in different properties, because if your band gap is increased, then there will be a change in electrical properties, there will be a change in magnetic properties, there will be other properties or physical properties has been changed. So this effect leads to rise in the energy of electrons within the conduction band, resulting the greater the spacer between the energy levels, and thus wider the band gap. If these electrons are reduced, then the wider will be the band gap. How to manifest? How to manifest the size? So we know normally if the particle size is less than 2 to 10 nanometers, then we call it as a quantum material. So as we said, first in a bulk semiconductor materials, the cube is large. Okay, it is in 3 dimensions. If you are removing, because it's a bulk bands. If you are removing your lone pair electrons, or if you are removing your electron hole pair, so the reduction of this band is decreasing. The bands are decreasing and the length is increasing, so that slowly from the bulk material to the size of the material will be decreased. And if the size of the material is confined to the 2 to 10 nanometers of size, then we call those as quantum dots, which is in 3 dimension. If still the size of these materials are decreased, then you will get a quantum voids and quantum wells. Okay. So these are a brief about a quantum materials. Normally, these are quantum materials are widely classified into different types. There are topological insulators, superconductors, 2D materials, quantum dots. These are the different types of quantum materials that we are focusing on. So basically, I was very expertise in 2D materials and quantum dots, and I'm new to these topological insulators and superconductors. So I will give you a brief discussion about topological insulators and superconductors, and I will go in details with these 2D materials and the quantum dots. So these topological insulators are also nothing but quantum materials, where its surface is conducting and its core is insulator. Basically, we have an insulator material or a conductor material. Never insulator material will become a conductor until it reaches to the TC point. But these materials are having a unique nature where core is a conductor, and the surface is insulator. Why? Because they are defined that there will be an surface is having a lone pair of electrons. So due to this, they extend their electrons to the holes, and the whole connection band to a valency band and valency band to connection band. It produces a conductivity on the surface. The best examples of these materials are bismuth, Bi2Sc3, or Bi2 titanium, titanium 3, something like that. We can have this alloy kind of materials are the best example for topological insulators. Coming to the next type of materials are called superconducting materials. We are well known about these superconducting materials because we have gone through different applications, and which is very booming sector right now in India, and it will be a very futuristic technology that I want to admire, and I want to develop my career in these materials. There is huge opportunities with these superconducting materials. Normally, what is this superconducting materials? The superconducting materials that exhibit superconductivity, and a phenomenon where they conduct electricity with a zero resistance below the critical temperature. So if these are very important in the present quantum computing and quantum mechanics properties. Basically, some metals like rare earth elements or some metals are the superconducting materials. We know there is no pure superconducting material, but niobium, aluminium, titanium will act as a superconducting materials in certain cases. And also there is some alloys kind of materials called niobium, titanium, niobium, aluminium are other examples for conducting alloys. Now coming to the quantum dots. Very fascinating material for the quantum materials. So quantum dots are nothing but nano crystals from conducting materials, nanomaterials, which size is around 2 to 10 nanometers. So if the size of the nanoparticle is between the 2 to 10, then we call that as a quantum dots. So this was discovered in 1980 and exhibits quantum configuration and performance with a high surface and high volume ratios. Normally, why we are very much fascinated about these quantum dots? Because of its applications. So it is we can use these quantum dots in various applications like semiconductors, carbon. We can use in energy storage. We can use in solar cell applications. We can use in other what is we call biological applications. So we can define these quantum dots in different types. Like we can use carbon quantum dots, graphene quantum dots, perovskite quantum dots. We can make a composite like boron quantum dots. We can make sulfur quantum dots. So it is easy to publish, easy to prepare, and vast applications, and so very defined. It is easy to define in our research papers. So these are most fascinating. We'll talk in detail in further case two about the quantum dots. I'll take one example of quantum dot, and I will explain you how to synthesize the quantum dots, and then applications of these quantum dots. Synthesis of quantum dots can be done in normally we have two methods: top down approach and bottom up approach. We can synthesize these quantum dots in the both the ways using arc melting or arc discharging, laser ablation using top down approach, and from bottom down approach we can do hydrothermal, pyrolysis, microwave, and other altochemical methods like sol gel. Now coming to fourth kind of materials, which is a very promising material, is 2D materials. 2D materials are the materials which having one atom thickness. So with atom arrangement in a flat sheets. These are the materials with the having of uh, two dimension, where it's a thickness is all about one atom size, and this all the atoms present in the 2D materials are arranged in a flat sheet. It has unique properties like strength, high strength, and conductivity due to their ultra thin structure. Normally, quantum dots are the 3D materials, 3D electronic configuration. But coming to the 2D material, they are having a 2D electronic configuration. That's why it is very thin and flexible kind of materials we can use for different applications. We can go for electronics, sensors, batteries, and flexible screening applications as well. So coming to different types of materials, different types of 2D materials. We know we have different types of 2D materials and its applications. So here are the different types of materials. HBN is one of the promising 2D material where boron and nitrogen are aligned with hexagonal structure. Black phosphates, molybdenum sulfates, graphites, amexines, uh, 2D polymers, 2D silicates also available. So these are the different 2D materials that are currently it is available in the research field. So why we need to use? So I'm taking an example of these 2D materials, and I'm deriving and synthesizing these 2D materials with the HBN and reducing graphene oxide, and I will show you the results for the battery applications. Let's see what's the need of quantum materials in the batteries, because I was working on batteries since 5 years. So I am switching from bulk materials to quantum materials for my application. Why? Because the battery materials are having some issues with the bulk materials. First one is in rechargeable materials. There won't be any certain uh, uh, capacity constant. Like we can say after certain period of certain cycles, our capacity fading is usually happens in the bulk materials. To avoid this capacity fading, and also the battery materials can sustain for particular temperatures. If you know that lithium, we have seen a lot of news regarding lithium ion battery car or bike has catch fire, because these materials are confined to certain temperatures. If you cross the temperature in Dhamma highways, there will be cause of firing or accident. So to control this, we are moving from bulk material to the quantum material, where the properties are unique and stable, even if the particle size has been reduced, which helps in higher the capacity, faster the charging, longer lifetime, as well as sustainable for environment. So now I'm moving to a crucial that device manufacturing, device fabrication from quantum materials. So I have taken a first case one. It is about high performance of HBN RGO selenium composite anode material for fast charging and high current density sodium-ion batteries. What is this HBN RGO selenium? HBN is a boron nitrate which is having hexagonal structure. Okay, a 2D material. Reducing graphene oxide is well-known material to all of us. So I'm preparing a composite using a 2D material, reducing graphene oxide and selenium, which is act as an anode material for energy storage applications. So how to synthesize these 2D materials? So well-known and very easy single step method we are following to synthesize the 2D materials. So normally, in recent research scholars or people who are very interested to do research. So the major confinement, the major problem or the major thing they are facing is synthesizing of materials. So for the synthesis of materials, you require a lot of machineries, what we say, furnaces, equipment. So these beauty of these quantum materials are we can do the synthesis of these quantum materials with a simple and affordable methods. Suppose hydrothermal. Hydrothermal we require only autoclave and a normal hot air oven, right? Which can be sustained up to 200 degrees is enough. So autoclave doesn't cross more than 10,000, and hot air oven doesn't cross more than 50,000. If any institutes who are want to synthesize something, do some research in fundamental research or synthesis process, but lack of resources, they can go for these low budget equipments. So we can synthesize these 2D materials, quantum dots, and many other metals using this hydrothermal method. So we can using the hydrothermal method. I have derived this 2D material composite, taking boron nitrate and reducing graphene oxide is 1:1 ratio, with boric acid as a source of boron source, and urea as a nitrogen source, and graphene oxide as a reducing graphene oxide source. Normally, reduced graphene oxide, we know that reduced graphene oxide is synthesized using humus method. Humus method is nothing but synthesizing of graphene oxide, maintaining your temperature at 4 degrees, and adding KOH in it and making into it, reducing graphene oxide. So from the humus method, we have synthesized the graphene oxide. I'm not going details about synthesis of graphene oxide because it is well known and well established. So I'm only focusing on synthesis of this 2D material. So first we weigh according to that particular ratio, and we mix it thoroughly with agate mortar, then transform into a autoclave, and put the autoclave in a hot air oven at 80 degrees. Sorry, it is 180 degrees. So 180 degrees, and you will get a fine powder. So the solution here, you will get a fine powder. So this fine powder was dried at 80 degrees and go for the calculation. So we'll get a composite. If you see this XRD, normally graphene oxide will get a peak at from 20 to 30 degrees, which is 002 peak that we were clearly identifying in here. So 20 to 30 there is a peak, and also there is another peak at 001. Sometimes where reducing graphene oxide is to have the peak at 10 to 15 degrees. So then if you see HBN RGO, which is a composite of HBN and RGO. I'm not talking about the selenium now. So in HBN RGO, you can see the reducing graphene oxide peak is highly reflecting in this composite. If you after doping of selenium in the reduced graphene oxide, which is a blue color, so there is a predominant of dominations of selenium, though there is a HBN and RGO. So this complex composite itself clearly shows that the selenium domination of selenium in the 2D materials and intercalation of selenium in this HBN and RGO composite. If you see these microstructural properties, like if you see this SM, so this first image of A representing only HBN network, which is looking like a vise, right? So this wire spider net kind of morphology. This fiber net kind of morphology is showing HBN, and the flaky kind of structure is showing graphene oxide, reduced graphene oxide. This bulk material representing the selenium. If you mix HBN, RGO, and selenium, this composite looks like this. That contains a fiber spider net HBN network with a flaky kind of graphene oxide, and in these two networks the selenium is uniformly distributed and rounded and becoming a fine crystal structure. You can see the same define this chem image also support the same information that selenium is incorporated in the HBN RGO network. You can see this kind of dark network is representing a wide kind of network, which is representing this HBN and RGO. In this kind of network, we can see selenium is incorporated properly in the network, which is reflected here, because these are the mostly having three phases. HBN is presented, RGO, and selenium. These three orbitals also observing in this kind of network with the spacing of 0.3 and 0.22 nanometers. Coming to the crucial energy storage applications. So to know whether this 2D material of HBN RGO based composite is used for the energy storage or not. First, before studying about energy storage, we will see the fabrication of coin cell. So here, fabrication of a battery. So in fabrication of a battery, we have different setups like lower cap, upper cap, separator, spacer, and active material. So using these, we will assemble a coin cell, and we'll go for the cyclic voltammetry for using that coin cell. So this is a cyclic voltammetry of HBN RGO selenium doped HBN RGO composite, 2D composite. So here clearly we can see that before cycling and after cycling. Before cycling, you can see the cyclic loop of the cyclic area of the cyclic voltammetry is around 1170 centimeters per cube. If you are after cycling, the area of the cyclic voltammetry has increased. That represents that the energy storage capability is increased after cycling performance. Initially, the redox peaks are we observe that oxidation and reduction peaks. The oxidation peaks are at 1.3 volt and 1.8 volt, and the reduction peaks are observing at 1.6 volt and 0.6 volt. So you can also see a small, a broad peak at 0.73 due to SCI layer formation, and also SCI layer formation means solid electrode interface layer formation. Due to that solid electrolyte interface interlayer formation, or else side reactions during intercalation and deintercalation of sodium ion batteries or lithium ion battery. This is a cyclic voltammetry at different cycles. See, all the peaks are overlapped each other. That means even at different cycles, this energy storage capability is constant. Usually, to study the electrochemical performance of any material, we'll go through different studies like cyclic voltammetry, galvanometric charge discharge, cycle index, as well as current rate, C rates. So here we are studying about galvanometric charge discharge. So this galvanometric charge discharge represents the line, a plot which is flowing from high potential to the lower potential, and this is called as a discharge of a battery. If the plot is flowing from the lower potential to the higher potential, that is called charging of a battery. Normally, we'll say that our mobile phone has charge and discharge. So when the battery is charging or discharging, its capacity will be reduces or at the time of charge, and the capacity is increases with respect to charging. So here we can see this plot having a wide rise up to this point, and there is a flat plateau here, and there is again a plateau here, and there will be a straight plot again at this moment. That means here you can represent two plateau regions are is formed, and also in discharge also you can see the same phenomenon. Here one plateau region, and here one more plateau region. Why? So here you have seen two peaks, right? Two oxidation peaks and two reduction peaks, and here also you have seen two plateau regions. This represents that there is a phase transfer at two times in the during oxidation and reduction process. So first phase transfer may be intercalation of selenium ions in the HBN, and later intercalation of HBN selenium ions in RGO. When this oxidation is happening at the potential of 1.5 volt and at the potential of 1.8 volt, this sodium ion coming and sitting in this integration process, so that you will get a capacity around 840 milliamperes at first cycle, and then 502 milliamperes at even after 500 cycles. We can study this oxidation reduction process and their properties of that sodium ion intercalation and the intercalation process using this reducing charge discharge profile, and this discuss representing this cycle performance of our battery. So if a battery is charged and then discharged, and again it is charged, it is discharged. So if a battery is charging for one time and discharging for one time, that is called one cycle. Charging and discharging happens if that represents one cycle. If a battery is charging for number of times, like 500 times, 1000 times, 3000 times, that terms we call as cycle index. So here the battery is charging and discharging for multiple times, then the capacity is sustained even after 1500 cycles. If you can see this line, this is very stable. There is no any drop in the capacity. That means its efficiency is 100%. We can see for this kind of 2D materials. So coming to this one, this is cyclic index for different, like you can see different materials. If you take only the HBM, your capacity is less than 100. If you take only the RGO, that is also less than 100. If you take the only selenium, that is also less than 100. If you make a composite of this HBN, RGO and selenium, your capacity is gradually increasing due to its confinement of its structure. Its electrochemical properties has been increased. Later, this curve representing the current rate with respect to cycle number. What is this current rate? Current rate is nothing but a rate of charging with respect to a current. So in the above studies, what is in cyclic voltammetry, in galvanometric charge discharge and cycle studies, we have followed a constant current, which is 0.5 ampere per gram. But now we are varying the current with respect to cycles. So first, at 0.5 milliampere of current density, our capacity is around 700 to 800 milliamperes of capacity. if you are increasing the current, gradually what happens? Normally, capacity will reduce. So for 1 ampere, for 1.5 to 2.5 till I went for 6 milliampere hour, milliampere per gram current density. The capacity is slightly decreased, and after coming back to 1.5 milliamperes again, I'm giving the same. First, initially I have increased the current to 6 milliamperes. After again I have given the initial 1.5 milliampere current density. So how much the capacity it retained back, that we call as capacity retention. The capacity retention is almost 98% of capacity retention has been noticed using this HBN RGO 2D materials. So just not I am not defined I'm not defining this research with the preparation of a half cell. I want to go for the fabrication of a full cell. How to fabricate a full cell? So normally in a battery containing a cathode material as well as anode material, there will be a separator in between them. We are assembling, we are taking a cathode as NVP cathode, which is commercially available for the sodium ion batteries, and I'm taking my HbN-RgOSC as an anode, and fabricating a full cell. So if you see the cyclic voltammetry of this full cell, or if you compare the cyclic voltammetry of a half cell, uh, it's almost similar. So after before full cell and after full cell, the oxidation reduction peaks are obtained at the same potential range. But the problem is you have a narrow peaks representing the high oxidation reduction, whereas this wide peaks represents a low oxidation rate in the full cell when compared to the half cell. So after I went for the charge discharge profiles as well. So initially, if it is a half cell, it's showing around 700 milliamperes to 600 milliamperes. But after sorry after preparing a full cell, it's also giving almost 70 milliamperes capacity initially, and it is reduces to 55 milliamperes even after 100 cycles. And this is a life cycle analysis for 200 cycles, and the capacity is almost constant after. Initially, there is a gradual decrease in the capacity, but later it is constant at 45 milliamperes of capacity with 99% of Coulombic efficiency. Then now let's talk about the case 2. Here they were interesting topic of quantum dots. So I have prepared quantum dots using a green synthesis method. So we know there are different types of quantum dots: graphitic quantum dots, carbon quantum dots, sulfur quantum dots. Different kind of quantum dots we have. So I have taken a carbon quantum dot. Why? Because I'm using this for the supercapacitor applications now. Before I have talked about 2D materials for battery applications like battery assembly. Now I have taken a quantum dot for the supercapacitor applications. Usually we can prepare the synthesis in different methods. We can take a raw materials like toxic materials or other sulfide based materials and other carbon based materials. But now I have taken a green synthesis method. I'm following a green synthesis method where we can take natural reducing camping reagents to create inorganic nanoparticles or quantum materials. Why? Why we are using a natural reducing agents? Then why we are not using other chemicals? So usually for environmental safety purpose, we will avoid this other chemical materials and going for the grain synthesis method. But there is another property that we need to notice, that the quantum dots or quantum or nanoparticles develop using inorganic materials or natural reducing agents like sugars, vitamins, materials. So they will form a polyphenol, so which is a primary source for building a components. So polyphenol is a material which is present in this bio waste, which builds the molecules and which builds the atoms in the natural method. Maybe this is the reason of existing this world. So we are came from the non-living material. So this kind of this is also one more process that involved to developing this development of atoms, development of molecules and the matter. So, but using the green synthesis method, there are some drawbacks like stability, toxicity, and solubility. Normally, if you take any other kind of natural reducing agents, there will be a huge problem with solubility. That's why I have taken a lemon juice, which is soluble in water as well as soluble in other ethanol, propanol, other alcohol materials. So I have taken a lemon juice. Then I squeeze this lemon juice into a water. Uh, then I have stirred for certain time for 1 hour. Then I put that stirred lemon juice in a hot autoclave and done heat treatment for 180 degrees for certain hours. Then that autoclave was thoroughly stripped and thoroughly washed and dried at a hot air oven at 60 degrees to develop a carbon quantum dots. This is the now I have taken this carbon quantum dots and I prepared I mixed with the boric acid to form borate dope quantum dots composites. To prepare this, I have taken 40 ml of lemon juice mixed with 400 mg of boric acid. That means I taken 1:10 ratio. 40 ml of lemon juice and 400 mg of boric acid. That means 1:10 ratio. Boric acid. Then stir it for regardlessly that for 1 hour. Then pour that in the autoclave and heat at a temperature of 180 degrees for 12 hours. So you'll get boron doped carbon quantum dots. This boron doped quantum dots, after stirring, we need to go for we need to wash it thoroughly using centrifuge at 10,000 rpm for 20 minutes. So we can avoid other materials or impurities in the carbon quantum dots. So later we went for the UV absorption, where we can see absorption peak at 260 nanometers and 330 nanometers, which is activating pi transition of a carbon and n pi transition of carbon double bond oxygen respectively. So this confirms the presence of carbon materials. And also I want to study these are quantum dots or not with its size, with the size. So I went for this SEM analysis. From that I have plotted histogram plots where that average particle size is, sorry, it is wrong here. Average particle size is 2 to 10 nanometers. 10 to 2 nanometers it is. I written as 10 to 12 nanometers. 10 to 2 nanometers. We can see after that, coming to the XRD and other microscopic structural properties, usually quantum dots, this is carbon quantum dot. Carbon having a peak between 30 to 40 and 20 to 30. 20 to 30, you can see a broad peak which is representing these uh, carbon, presence of carbon, and then this high intense peak in this representing its crystallinity in the quantum dots, carbon quantum dots. And after doping of a boron in the quantum dot, you can see a high crystalline material which is highly due to highly reflecting these boron concentrations in the carbon quantum dots. You can see spherical structures of quantum dots in the same initially. Even if you see high magnification as 500 nanometers, a clear small spherical drops or we can see here, which is representing the carbon quantum dots. After this is boric acid SEM. After mixing these quantum dots and boron, we can see a network of quantum dots, which is carbon quantum dots, which is filled with boron. It is filled with the boron. So, after studying these microstructural properties, now let's see the electrochemical performance of a supercapacitor. So I told you that I used these boron quantum dots for the supercapacitor applications. So if you see these cyclic voltammetry loops, so at different voltage swipes, for 10 millivolts, for 25 millivolts, for 50 millivolts, 100, and like up to 200 millivolts. When I'm sweeping the voltage for higher voltage, the area of the loop is increasing, and the reduction peak at 0.2 volt and oxidation peak at 0.4 volt is reflecting heavily. That means when the sweeping of voltage is happening, so the polarization between these polarization in the supercapacitors is increased with respect to voltage, and reduction and oxidation redox reaction is happening at 0.2 volt, and reduction reaction is happening at 0.2 volts, and oxidation reaction is happening at 0.38 volts for different materials. This is just quantum dot material. This is for boron doped quantum dot material. So if after boron doped quantum dot material, you can see the more area of a loop, the increasing in the area of the loop. So more the area of a loop, more the energy storage capability in the supercapacitors. So then went for the GCD. Initially, my discharge capacity is happened at 180 seconds. Then the second discharge capacity happened at 120 seconds. That means the all will get almost 200 to 300 farads efficiency capacitancy. So later I went for different studies. Went for different cycle performance of this supercapacitor. So I went up to 10,000 cycles for the supercapacitor. The Faraday retention ratio is almost 98%, and also the capacity is 550 to 600 specific capacitance. Even after 10,000 cycles for this quantum boron doped quantum dots. After that, I have calculated the energy density and power density, because normally the supercapacitors will give you huge capacitance initial, but when you consider that into an energy density where for the commercial purpose, so it will drops gradually like this. This is the most disadvantage of the supercapacitor we need to address for the future. So the power density is gradually dropping down with respect to the energy density is increasing. It run up to 10,000 cycles and sustain for 94% of charge retention even after 10,000 cycles. These are the two cases of using quantum materials. First case is I have prepared 2D materials and use it for the battery storage applications. In second case, I have prepared a quantum dots, use it for the supercapacitors. So from these two cases, I would like to conclude that our quantum materials having very good applications in energy storage as well as superconducting materials and also batteries and quantum computing and other advanced materials, other advanced technologies. So what will be the future of these quantum materials? So quantum materials quantum materials has very vast applications. Like maybe we can go for the hardware platforms as well as the software platforms. So usually now quantum it is a great move that in recent years there is no much development in the hardware sector. So these quantum materials can give a boost towards the hardware platforms as well as a software. And as a physics student, we can as a physics of people. So we also have wide channels for the further research in these quantum materials. So I would like to say bye for the nanotechnology and move for the quantum technology. Thank you for everyone for giving this opportunity. Thank you, ma'am.
Thank you so much, sir. Dear participants, if you have any queries regarding the session, you can unmute yourself and ask questions. Any queries, please?
If there is no queries, means if they well understand or they didn't understand.
Hello.
Ah, yes.
Hello, sir. It's a very nice presentation. Thank you. Yeah, I have a query regarding fuel cell. One of your slide you have shown that you have also worked on fuel cell. So, yeah.
Yes.
So, what kind of material you have used for the preparation of the fuel cell?
For the preparation of a fuel cell, I normally battery having three parts: cathode, anode, and electrolyte. Usually, people used to work only on the cathode materials or only on the anode materials. They will study all electrochemical performance of that particular electrode. But I have developed a fuel cell using NVP, sodium vanadium phosphate as a cathode, and my composite HBM RGO selenium as an anode material. So I assembled using I taken this electrode coating on the aluminum foil and this electrode coating on the copper foil, and I assembled the parts.
So, between the anode and cathode, there is a membrane, right?
Yes, yes.
So, I mean, what kind of membrane it is?
Basically, we use that that we call as a separator, sir. Watchman filter paper. So Watchman is a company which derives its separators, which is having a porosity of around 20 to 30 nanometers.
Okay. So it is purchased, right?
Huh? Sir?
It is purchased?
Yes, yes. It is
This is
one.
common. Okay. Right. I mean, I just want to know. I mean, do you have any experience on a polyelectrolyte, which can also be used as a?
Yes, sir. I have prepared. I have experience in solid electrolytes as well as liquid electrolytes, sir. I have synthesized silicate-based solid electrolytes.
Right.
Where gadolinium, IgM are the rare elements which is substituted in the solid electrolyte network. And as Nascan type electrolytes, I have prepared. Also, I have prepared sodium perchloride doped, mixed with EC and PC in 1:1 volume ratios and all.
Okay.
This is a liquid electrolyte.
Okay, then I will go to your, I mean, some publication, then I will get the more information.
Sure, sir. Thank you.
Okay, thank you.
Ma'am, any questions?
If anybody have queries, please ask Dr. Vamsi Krishna Garu. I hand over this session to Dr. Radhika ma'am for the vote of thanks.
Distinguished guests, respected colleagues and dear participants, good morning to everyone. I, Dr. G. Radhika, Assistant Professor of Physics in the Department of Humanities and Science in Reddy College of Engineering. As we come to close of this enlightening faculty development program on an incremental action for quantum materials to quantum devices, it is my privilege to extend a heartfelt vote of thanks to everyone who made this event a success. First and foremost, I would like to express our deepest gratitude to Dr. Vamsi Krishna Katta for sharing his extensive knowledge and valuable insights with us today. Sir explained on the quantum confinement explanation and what are the classification of the quantum materials like topological insulators, supercapacitor, two-dimensional materials, quantum dots and their applications, and the quantum dots which are used in solar cells, EVs and lasers and used in displays. The explanation is very nice, sir. And how the synthesis of the quantum dots need for the quantum materials and batteries, and what are the characterization techniques like XRD, SEM and TEM, electrochemical performance, and microstructure studies explanation is very good. And also the very important point in this section is the green synthesis of the carbon dots from lemon juice and its application in supercapacitor. So your presentation was truly inspiring and has provided us with a deeper understanding of the latest developments in quantum materials. Thank you for your time and for being a part of this program. I would also like to thank our principal sir, Dr. M. Ashok Garu, and HOD ma'am, Dr. Sneha Joshi ma'am, for their continuous support and encouragement. Your guidance has been instrumental in organizing this event and fostering an environment of academic excellence. A special thanks to the organizing committee and all the staff members whose hard work and dedication have made this program possible. Your efforts behind the scenes have ensured that everything ran smoothly. I am also grateful to all the participants for your active engagement and enthusiasm throughout the section. Your presence and participation have greatly enriched the discussions and made this event truly interactive and beneficial. Lastly, I thank each and every one of you. You are attending and contributing to the success of this faculty development program. Let us take the knowledge and insights gained today and apply them in our respective fields to drive innovation and excellence. Thank you once again, and I wish you all the best in your future endeavors. Thank you, sir. Thank you, Dr. Vansi Krishnan.
Dear participants, feedback form is available in YouTube and as well as in Google Meet chat box. You can fill the feedback form and you will get the certificates. We are going to wind up this session. Everybody can fill the feedback form and you will get the certificate. Thank you so much. Thank you, sir.
Thank you so much for having me.
Thank you. Thank you, sir. Sir?
ಅದು ಮೇಡಮ್ ಇರ್ತಾರೆ. ಗ್ರೂಪ್లో వద్దు.